Okay, guys, I'm going to go ahead and get started. Can everybody hear me okay in the headphones? All right, I see at least one nodding head. Thank you very much. My name is Dan Griffin. Thank you very much for coming to my session. This is Amazon FreeRTOS Security Best Practices. It's going to take a little bit of a twist from probably what you've been seeing for most of the rest of the conference. Talk more about IoT on the device side, get all the way to the edge, as it were. Let me introduce myself briefly. I'm a senior software engineer on the Amazon FreeRTOS team in AWS. I've worked at Amazon for about 2.5 years. I joined the team shortly after AWS acquired the FreeRTOS kernel, and I'll introduce FreeRTOS in a little bit more detail in a couple of slides. But in any case, before I joined the FreeRTOS team at AWS, I worked as a security consultant for several years, working with other software companies, typically on multi-factor authentication features for their software and that kind of thing. And then before that, I worked at Microsoft on one of their security teams. Okay, so let's talk about the reason for being here, the reason that this matters. Whether you're a manufacturer of connected devices or an IoT solution operator or a solution integrator, let's say, your fundamental responsibility is to retain customer trust. And retaining customer trust takes, it means covering a lot of different bases. For example, it means maintaining uptime and availability and reliability for your solution. It means minimizing service disruption. It means managing costs so you can pass those savings on to your own customers and pay your employees. It also means responding to demand for new features and capabilities, and including cool stuff that your customers may not have even thought of. Equally important is ensuring the privacy of your customer data, as well as the confidentiality of your own proprietary business data. You need to cover all those bases not only to retain customer trust, but frankly to stay in business. So the security best practices that I'm going to cover in this presentation cut across all of those customer trust factors that I just listed. And my point is that following security best practices is an enabler for your business, and really talking about them that way is the way that you get those efforts, the way that you get that, investing in security, the way that you get that justified to your own management. And again, security is an enabler for every aspect of retaining customer trust, which in turn is a requirement for business. So I mentioned that I'm on the Amazon FreeRTOS team. FreeRTOS is a real-time operating system that was acquired by Amazon, let's say about 3 years ago. FreeRTOS is a tiny real-time operating system that basically consists of a scheduler, some support for tasks or threads, support for some queue-like messaging features. Again, it's tiny, and we're talking about devices that have on the order of 128K of RAM, if they're connected to the cloud and need to do TCP/IP and TLS, or if the device is not connected or is only indirectly connected to the cloud via an edge device, you could be talking about much less RAM than that. The Amazon part of Amazon FreeRTOS, at least in terms of my own model of the product, is this set of connectivity libraries that my team has been contributing to Amazon FreeRTOS and to our open source repository over the past 2.5 years. And the idea behind those libraries is to allow embedded device developers to get connected to the cloud or indirectly to the cloud via an edge device, via whatever transport, quickly and securely. And so I'm going to talk a little bit about how kind of some of the security basics roll into doing that connectivity across the board in terms of kind of the end-to-end of your IoT device solution lifecycle. I introduced Amazon FreeRTOS. I think the last thing I'll mention is that I do encourage you, at the end I'll have a few more pointers for how to run the demos yourself. But if you're interested, I do encourage you to clone our repo out of GitHub and check it out for yourself. You actually do not need to have any IoT hardware just to try to run the kernel and the scheduler and to connect to AWS IoT. You can do that all from a simulator, and it's actually the simulator that I'm going to use for my demo, in fact. So I'd like to talk about Amazon FreeRTOS and connected devices and IoT solutions in general in the context of these 6 key elements of security. I don't know if any of you just came from my presentation with my colleague Momina. I apologize. This part is going to be pretty similar to that presentation, but I'll get into a bit more detail in a few slides. So by way of introduction of each of these 6 key elements, appropriate credentialing refers not only to the identity of the devices and principals of your IoT deployment, but also the procedures that you use for creating those users and roles and devices. And that dovetails into secure onboarding, which is the process that you use for kind of bootstrapping that connectivity. So getting your IoT devices connected and configured in your deployment in a way, most importantly, that protects your sensitive data, again, throughout the life cycle, all the way through to the end of the life cycle of that hardware. Over-the-air updates, or OTA, refers to the ability to deploy new firmware images from the cloud to the device. But it's more broad than that. It's not only deploying new firmware images, it's also rolling new credentials, new client certificates for your devices. And it also includes servicing the peripherals of your device. For example, you might have like a Wi-Fi radio that you need to update, or a sensor firmware image, or an FPGA or something like that. All of those images or objects can be serviced via OTA. Monitoring refers to your ability to, in your IoT deployment, as the operator, to know at all times what's going on in your deployment. Oops, sorry. I clicked the wrong button. Auditing refers to ensuring that the security best practices and the security policies that you've instituted in your organization, that those are actually being followed, and that if and when you do have a deviation from that policy, and frankly, when I was working as a security consultant, you inevitably see policy drift over time. That's the purpose of auditing, is to bring those policy elements back into compliance in your operations. And finally, remediation refers to your ability to do just that. In fact, it's 2 things. One is, you've done an audit and you've seen that there's been some deviation from policy. You're going to remediate and remove that deviation from your operations, make sure that you're following policy across the board. But not only that, the second half of remediation is that you're going to try to make sure that you update your operations in such a way that that doesn't happen again. Let's drill into appropriate credentialing. So consider end-to-end operational security for your IoT solution based on best practices for identity and access management. And what I mean by that is that I think the key point when we're talking about security best practices is that fundamentally there's nothing really new. Security best practices apply to classical enterprise PKI, classical enterprise IT, client-server security, really in the same way that they apply to IoT. You could argue that there definitely are some differences, some different challenges in IoT. That's one of the reasons why I enjoy working in the IoT field right now. For example, you tend to be talking about, across all of IoT, a really very heterogeneous set of hardware, heterogeneous use cases, a lot of different connectivity protocols versus local, in terms of local connectivity and consumer and industrial scenarios. So there's some differences, but let's not forget the basic block and tackling of security, and those things still apply. And that's the point of these 6 elements, appropriate credentialing being the first one I want to talk about. And I'm going to switch to my demo machine here, and I'm going to talk about appropriate credentialing in the context of 3 different types of roles that interact with my IoT deployment in AWS IoT. The first being my interactive administrative users, of which I am an example. I'm logged into the console here as an administrator. And you can see a couple of things in the console window that I'm showing here. This is in the Identity and Access Management console, or IAM. First, you can see that I'm not using multi-factor authentication, at least not the built-in multi-factor authentication feature of IAM. In fact, I am using multi-factor authentication. It's just that I'm doing so via federated authentication. So it's only via my corporate federated token server that I can get into this account. And that, again, does enforce strong authentication. But if you're not using federated authentication, you should be using multi-factor authentication to protect your admin accounts. So that's one thing that's potentially showing as, let's say, out of compliance or risky in this console view right here. The second being, this gray text is much harder to see, but in any case, you can see that I last signed in with this particular account 304 days ago. And that's indicative of a potential risk, because this is showing that this is an account that might not be in active use anymore. But nevertheless, if you look at the access advisor for this account, I have to scroll down to see all the rights that this account has. It basically has admin across the board. And so this is an account with a lot of access to my IoT deployment and AWS in general. And it's an account that looks like it might not be active anymore. So this is a pretty risky, this is evidence of some risk here that I might want to, for example, disable this account and make sure that it's no longer being used, make sure that nobody complains, and then ultimately delete this account if it's no longer being used in order to eliminate that risk. Okay, back to the slides. I want to talk to, in the context of appropriate credentialing, I actually want to talk about two other kinds of access to your AWS IoT deployment. One is script-based access to your control plane. So you're probably, once you go to scale, you're probably not going to be making every administrative change manually in the console. You're probably going to be automating some of those things. That would for sure be a best practice to ensure that there's less likely of human error in that case. The trade-off is that, and again, switching back to the AWS IAM console, the trade-off is that as part of supporting that programmatic access for your scripts to your control plane, you're very likely to have some shared keys out there. It's these access keys that you're probably using for your script-based access today to AWS. And again, those access keys are something that I encourage you to audit the use of. So make sure you know exactly what access keys are currently active in your account. I'm listing 2 here in my account. And similarly to the interactive user that we just audited, we want to look at when this key was last used. So this key was last used this month. This would appear to be one of my active keys. But the second key hasn't been used since January. And so I suspect what happened is that this key is associated with one of my laptops that I may have traded back into corporate, or that may be sitting at home somewhere. But in any case, in a production environment, that would for sure be a risk, because you've got basically a computer sitting there with a hard disk, with an access key sitting on that hard disk, and that access key has a lot of rights to your production environment, let's say. So that would be, again, be a situation where in order to remediate or reduce that risk, you would probably temporarily disable that access key and then eventually delete it. Okay, so that's the second category of appropriate credentialing. The third category of appropriate credentialing I want to talk about is the devices themselves. And typically with AWS IoT, we encourage you to provision your devices with X509 client certificates. And I want to show an example here of how those are administered. I'm switching to the IoT console. I am clicking on the Manage tab. I'm clicking on the Things node. I'm clicking on my Reinforce device, which is what my simulator is running that I'll show in a bit. And this Reinforce device, if I click on the Security tab for this device, has a certificate associated with it. This is the SHA-256 hash of the client certificate that's been provisioned for my simulator device. So if I click on this certificate object, which again is an object that's in the IoT Core registry, the last thing I want to show you here is the policy that's associated with this certificate. And what this policy tells you is that any device that's able to authenticate with this certificate, which happens to be my simulator device, is going to be granted these rights expressed by this policy. And you can see that this policy has a reasonably constrained list of rights. These happen to be kind of more or less the basic set of rights required in order to run the Amazon FreeRTOS demo code that you would find in GitHub. I'm specifically running the OTA demo application, which I'll show again in a bit. And just to summarize what this policy says, it is basically saying that the owner of this certificate, if they're able to prove possession of the private key, has connect, publish, subscribe, and receive rights on the MQTT topic namespace expressed by those resource strings. And those resource strings, the GUID that's in that resource string, this is the GUID actually for that Inforce device. So basically I'm giving the Inforce device rights to basically do just about anything on its own MQTT topic namespace, which is more or less what I've intended. You could restrict these further. Okay, back to the slides. Just did the demo, skip that. Let's talk about secure onboarding. The reliability and efficiency of your onboarding procedures are a very important consideration in ensuring that your authorized devices and the users, in other words, the kind of 3 different categories that I was just talking about in appropriate credentialing, you want to ensure that each of those devices and users has access to the production resources that they require exactly when they require it, and only exactly the set of resources, right? So you don't want it to have access to anything that it shouldn't have access to. For example, I'm giving my device access to a little bit more of its MQTT topic namespace than it needs. That could be locked down. I'm giving my administrative account access to a lot more than it needs. That should be locked down, right? So that's an example of giving access to a little bit too much. And that account that it looks like I haven't, actually there are a couple accounts in there that look like they haven't been used in a while. That's an example of giving them access for longer than the period of time that they need, right? So those are kind of negative examples, so to speak. Regarding secure onboarding of IoT devices, AWS IoT supports a variety of mechanisms for getting your devices registered with IoT Core. I'm going to demonstrate one of those, which is called just-in-time provisioning. Again, back to the demo machine here. I'm going to pop out of my policy view for my demo device. And instead of the list of things in my registry, what I'm going to show you here over on the Secure tab in the IoT Core console is I'm going to show you the CAs, or Certificate Authorities node. What you see here is the SHA-256 hash of 2 separate certificate authorities that I've registered in IoT Core for the purpose of just-in-time provisioning. I'll just click on one of them. This is obviously something that I've created for lab testing because it kind of has some made-up issuer and subject names there that you can see in the certificate properties at the bottom of the screen. But in any case, the way just-in-time provisioning works is it allows you to use either your own enterprise PKI or some third-party outsourced PKI, which we find is common among IoT customers for the purpose of external deployments. Or you can even use some of the AWS cryptography features to create a certificate authority, the purpose of which is to issue trusted client certificates to each of your IoT devices. And by introducing that certificate authority as trusted in the IoT registry, basically what's happening is that when each of your devices that has one of those certificates presents that certificate for the first time, so the user takes their connected Bluetooth toothbrush out of the box, and that toothbrush is going to onboard by connecting, let's say, either via your smartphone or directly to the cloud, to set up your settings, right? The first time that smart toothbrush connects, it's going to present this client certificate, and it's also going to present the CA certificate. And the CA certificate is going to allow that request for the first time to get routed to the appropriate account, which is my account here that I'm showing. And then second, that toothbrush is going to do TLS mutual authentication with the MQTT broker and IoT core. And successful completion of that challenge response protocol is going to result in that, in basically on the fly, that toothbrush being provisioned as a known device into the IoT registry. And so again, that's what just-in-time provisioning lets you do, starting with creating a certificate authority and registering it here in IoT core. And so now, each time when you issue 1 million certificates to 1 million toothbrushes, each one of those toothbrushes can automatically be provisioned without some a priori thing having happened somewhere in your supply chain to create those entities in your registry at an earlier time. We find that ends up being a much more scalable approach, much more palatable for our customers to get devices onboarded that way. Okay, back to the slides. Just did the demo. Let's talk about over-the-air updates. So the ability to deploy, maintain, and operate microcontroller-based connected devices securely and at scale is the reason that OTA is such an important feature for Amazon FreeRTOS. I will say that OTA presents both opportunities and challenges. To give an example of opportunities, take the consider like some appliance manufacturers. The appliance manufacturers can use OTA to roll out new features and new capabilities on the fly and delay hardware obsolescence. So if you're talking about like a smart dishwasher, a future firmware update to that dishwasher could allow it to operate more efficiently, use less soap, use less water, use hot water more conservatively, that kind of thing. Or for example, for industrial automation, there might be new programmability, models that an OTA update can enable without having your customers having to replace the hardware itself. So that's goodness. An example of a challenge is, suppose you're operating a group of hotels, and you've got smart panels in each room of each hotel, and you need to do a firmware update to those smart panels. But over time, across each of those geographic regions, across each of those hotel sites, you've had some hardware evolution. You've had to switch some suppliers at some point for some of the components on your board. You might also have had previous generations of firmware for which an OTA either failed or was not performed. And so as part of rolling out a new firmware image, you have to test and anticipate the fact that A, you're operating in different geographic regions, B, you might have different generations of hardware, and C, in terms of firmware version, you might be doing A to B to C to D, or you might be doing A to D. And again, that can be a very complex test matrix to work through as you scale out your OTA deployment. So that's an example of one challenge. Another challenge, and actually something that has actually come up with some of our customers, is, suppose you've got a smart lock, something that's commonly used, at least I've seen, in vacation homes. Let's suppose you've got some vacation homes in an area that has been hit by a hurricane. And what you have there is a situation where you could have like kind of the perfect storm, to take an unfortunate pun, but not only have you had a natural disaster, but you might have a situation where you have an urgent firmware update that you have to roll out because there's been a public security vulnerability announcement on some major protocol or something like that. So in order to retain customer trust, which kind of is the whole motivating factor here, as I talked about at the beginning, your customers are counting on you to patch that major vulnerability. But at the same time, you're in a situation where, because of the natural disaster, you likely have very spotty network connectivity. Cellular is likely to be up and down. Broadband is likely to be up and down. Not only that, but people are likely to be away from their homes, right? Because they don't want to be there when there's still kind of damage assessment being done, the area is still being rebuilt. So how do you plan and scale as the solution operator your OTA rollout in that situation? What failure rate are you going to have to anticipate in order to do retries? What threshold are you going to have to set knowing that there are going to be a certain number of devices that are probably just not going to be serviceable within the usual time frame that you'd expect, but nevertheless you want to continue with your rollout to get as many as you can. Balancing the risk between what could be actually a real bug that's being encountered versus just some network glitch. There's a lot of subtlety in there. Okay, so let's switch to the demo computer and talk a little bit more about OTA. What I'm going to show here is this is the OTA demo application that I've cloned out of GitHub. Our simulator actually just runs within Microsoft Visual Studio. And it consists of all the same code that runs on the device, except, of course, kind of for your bottom layer of drivers, where those drivers tend to be hardware specific. So in this case, we've got a storage driver for the simulator that can just write to the local disk. Whereas on your device, your storage driver would probably write to flash, for example. And basically what the simulator consists of from the FreeRTOS perspective is it consists of the scheduler. So the scheduler runs in a thread in Visual Studio, and it uses all of our connectivity libraries as usual, including even our TCP/IP library, which injects packets via an open source product that we use. It's called WinPCAP, if you're familiar with that. And that allows us to inject packets into the host operating system. So again, we're able to test like 95% of the embedded software stack in a simulator in a way that I find to be, it tends to be much quicker to debug that way. I'm going to talk a little bit more about the trade-offs of that approach in the end when I give you some more pointers for running the demos. But suffice to say right now what I'm going to do is I'm going to run the OTA application in the debugger, and it's going to bring up the network. And then what I'm going to do is I'm going to actually create an OTA job. And oops, what I need to do is pop back out to the AWS IoT console, top level here. I'm going to go back to the Manage tab where we were at the beginning. I'm going to click on Jobs. What you see here are 2 OTA jobs that I completed earlier in the day when testing. I'm going to click the Create button to create a new job. I want to create this middle one here. This is an Amazon FreeRTOS OTA update job. I'm going to select the device, which happens to be the one I'm running in the simulator right now on this same laptop. That's my Inforce device. And I scroll down here. I click Next. I'm going to select a code signing profile. This is a super important detail from the perspective of security and risk mitigation. By default, Amazon FreeRTOS OTA jobs require code signing. So that means you've got a certificate and private key somewhere on your operational side. And you're going to use that private key to sign the actual firmware payload itself. And the OTA console, the job manager, is actually going to do that for you. And then when the device receives that signed firmware after downloading the whole thing in chunks over MQTT, the last thing that the device is going to do before rebooting into self-test mode is it's going to test that signature, A, that the hash checks out, and B, that the signature is actually from a trusted signer. In other words, you're going to create that firmware at manufacturing time with one or more trusted signers programmed into it or somewhere in your configuration in Flash. And the device is going to require each subsequent OTA to be signed by one of those trusted signers, one of those trusted code sign certificates. And that gives you a lot of power over controlling who has access to, for one thing, create and output firmware binaries, let's say out of your CI/CD pipeline, as well as who has access to the OTA job console itself. So you have a lot of very granular control over being able to push firmware, new firmware updates out to your IoT production environment, which we think is very important because, frankly, in OTA, there's a lot that can go wrong. So something that needs to be very well controlled, very well tested, operated very methodically. And that's one of the reasons why we think that code signing is a very important feature of OTA. So I'm going to select the code signing profile that corresponds to this device. That's this Inforce profile here. I'm going to select a firmware image which I previously built earlier in the day. That's DCG Inforce here. You can see that this is a This is a binary that was output for the simulator because it was built by Visual Studio. It's a Windows executable. It just happens to be running the FreeRTOS kernel. And I'm going to select that firmware payload. And this last text box entry here is something that's platform specific. So the job console knows as part of my signing profile that I'm targeting the simulator. And therefore it knows that it needs to prompt me for what the name of the firmware image is that the device should write onto its local storage as it's downloading the firmware chunks. And I'm just going to use the same name as the original firmware binary, this AWS demos.exe. And then finally at the end, what that lets me do is once the download is complete and the signature check is completed, I can actually just manually run that downloaded image to complete my lab test of OTA and ensure that when I run that image, that's kind of simulating your real hardware, phoning home and saying, hey, self-test succeeded, everything checked out, OTA Device Manager, you can mark this job as succeeded. I need to select a role for the OTA Job Manager to use to assume on my behalf. There are several operations that happen asynchronously here once the job has been created, including, for example, reading that firmware image out of S3, including using the private key that I have in AWS Crypto and AWS Signer on my behalf in order to sign that firmware image, write that signed firmware image back to S3, create an MQTT stream out of that firmware image, and then stream that image over an MQTT topic that the device knows about. All of those operations need to be possible for this role to perform on my behalf. Best practice would be to give the role exactly those permissions and no others. And as part of our OTA documentation, we actually literally provide that policy that you can just kind of copy and paste in your role. Anyway, I have a role that I've already created by doing exactly that. OTA Job Role. Click Next. I want to give this job a unique ID. I usually just use some variation of a timestamp for that. We're going to create the job. Job creation succeeded. I can see up here in this little green text that the job is in progress from the perspective of IoT device management. I can also see here that there is one job, one firmware item that's been queued for the device. And now what the device is going to do, kind of summarizing what I've already been explaining, is that the device is receiving the job document from IoT device management over MQTT. The job document is a JSON document. The device is going to pull apart that JSON document and find the name of the MQTT topic that it's going to use to download that firmware image. It's going to download that firmware image by default in 1 kilobyte chunks. And then once each of those 1 kilobyte chunks is downloaded and written to local storage, the device is going to do a firmware check on that, a signature check on that firmware image. If the signature check fails, the default behavior, and of course you can change all this since it's open source, but in any case, if the firmware check, if the signature check fails, the device is actually by default just going to delete that image. It's not going to proceed any farther if the signature check fails. Another check that is treated similarly is that we, by default, don't allow the device to roll back to an earlier version number. And so your application version numbers for OTA must increment or they'll be rejected by the OTA agent on the device. Now again, you can change that, it's open source. But what we've seen flagged by many of our customer AppSec teams is AppSec will say, hey, a common use case for OTA is that you're patching a security bug. And so we don't want a user, let's say, to be able to reintroduce an older version of the firmware because it probably has unpatched security bugs in it. And so the compromise then is if you need to be able to roll out an older version of your firmware, you either need, as I mentioned, you either need to change the OTA agent to not prevent that, or more likely what I would encourage is you basically just need to take that older version of the firmware and you need to bump up the application version number and then re-sign and then redeploy it. Okay, so much for OTA. I already gave a lot of the technical detail of Amazon FreeRTOS of the client agent. I think there's one other thing I'll point out. In the second bullet item there, the way the OTA agent is architected in Amazon FreeRTOS is very intentionally done so that we minimize our RAM footprint. And what we found fairly early in our testing in creating our V1 a few years ago is that if you're in a situation where you have a bunch of different kind of tasks or operations happening in your, in a very resource-constrained device, and you get into the situation where you have to have more than one network socket handle open by your application or by one of those shared libraries, and you're on like a 128K RAM device, you're quickly going to eat up all your RAM just in network socket context space. And so for that reason, what we did is we structured all of our shared programming interfaces, all of our APIs, including OTA, in such a way that they can actually share the same network context handle as the app. And so you only have one TLS context, one TCP/IP context across all of your firmware image, if you choose to do it that way anyway. And likewise, all of your data plane can be over MQTT. Now, OTA can also be serviced over HTTPS. And so you could have, for example, some data plane or command and control operations happening with your device over MQTT, while you're also downloading an OTA image or something else, right, for your operations over HTTPS. But inevitably, you're going to incur a lot more RAM cost if you're running TLS on your main MCU, just because of relative to a typical embedded application, how much RAM is needed in order to do TLS. So that's the situation we wanted to avoid, just because of how relatively expensive RAM is on embedded devices. Okay, let's talk about monitoring. The goal of monitoring is to understand at all times what's going on in your production environment. And so in order to achieve that in a practical way, you need to know what resources you're going to monitor, what events you're going to look for and what you're going to filter out, and what tools you're going to use. You also need to assign some level of responsibility and an escalation plan. Who's responsible for doing the monitoring, and what do they do when something goes wrong? An example is how would you monitor the OTA job that I just created. And I'll switch back again to the demo in order to show the CloudWatch log activity that happens over the course of my AWS IoT device operations. I'm going to click on the logs group here in CloudWatch. I'm going to click on the AWS IoT logs v2 log stream. I'll click a recent stream here. I'll click this trace. And what this trace is doing is telling me is basically it's saying there was a publish operation performed by the device by this account ID. And let's see, does it say the device name? Yes, it says. I don't know if you remember, but this is actually the device GUID that corresponds to my device ID. I recognize it from creating that policy, but it also gives the device friendly name as well. So anyway, what happened is that the device published an update over the course of servicing that OTA, and that update operation in MQTT is logged by the AWS IoT MQTT broker into CloudWatch, so that should I need to go back and audit what happened as part of my OTA or to try to figure out if something went wrong, I have all these log lines to follow the OTA all the way through via each MQTT operation that happens between each of your devices and the broker. Okay, that was our monitoring demo. Let's talk about auditing. Auditing starts with establishing security policies, and it's only once those policies in place does auditing really mean anything, because otherwise you're doing an auditing, but you don't really know what you're measuring against. You don't really know what you're checking for. I recommend that you base your security policies on many of the security best practices that we're talking about now, as well as the security best practices that are recognized by your, for example, IT organization or by your operations organization. You also want to base your auditing requirements on your data protection and the business continuity requirements of your organization. So again, there's some common stuff here, but there's also going to be things that are specific to your customer base or to your own employer. Once those policies are in place, then you can use auditing to detect deviations from those policies. So I'm going to give an example here in AWS IoT of conducting an audit. I'm going to switch back to the AWS IoT console. And I'm going to show some previous audits that I've conducted using Device Defender. I'm going to click on the Defend node here in the IoT console. Click on Audit, View Audit Results. I'm going to look at a previous audit that I did that found something very interesting, something that I was doing wrong in my IoT deployment. That's this audit here. What's interesting about this audit is that it found that I was doing two specific things wrong, or let's say contrary to best practice. One is there's evidence in the AWS IoT registry that I actually have two or more devices that are sharing the same client certificate. And that's flagged as an audit policy violation. And that's the first entry you see here in non-compliant checks. And then the second entry you see here in non-compliant checks is that I have one or more IoT policies that are overly permissive. And actually, I've already, at the beginning of the presentation, I showed you a lot of policy settings that were overly permissive on my IAM accounts. And what Device Defender is showing me is that I have a similar problem here in some of the policies that I've created in my registry. We're going to come back to that in a second in the context of remediation. Let me switch back to the slides here. So the point is that as soon as you identify a security policy violation, you should remediate it. And in order to maintain data confidentiality and the integrity of your IoT deployment, you want to ensure that not only that you can remediate it, but that you're notified very quickly and that you can remediate very quickly. But there's a flip side of that, because you don't want to be making production changes recklessly or hastily. Instead, you want to test a policy fix or remediation just like you would do a measured rollout of, say, an OTA update. And in parallel, I think that the second half of remediation, the first half being actually fixing the problem, is that you want to make sure that the problem doesn't occur again. So you want to analyze your business operations, and you want to figure out what allowed that policy violation to occur and what you can do to prevent that from happening again. So let me show the last little bit of the demo, and then we'll talk about how you can run these on your own. In the same screen, we were just looking at the Device Defender audit report here, and these two non-compliant checks that I have. I want to click on the first, this being that I have a shared device certificate. And the remediation step is basically being described to me here by Device Defender, and that's in the mitigation here. And what Device Defender is telling me to do is, hey, the problem is that you were sharing a certificate across two devices. The mitigation is to stop doing that. And more specifically, though, not only do you want to stop using that certificate on at least one of your devices, you actually want to stop using that certificate entirely, because the exposure of your private key has been such that your best mitigation, your safest mitigation at this point, would actually just be to re-enroll all of the affected devices and start with a clean private key and a clean certificate. And then once you've ensured that those re-enrolled devices can connect, then you're actually going to delete that old private key and certificate from the registry. So that's the mitigation step for the mistake that I made in my operations here by sharing a private key and certificate across 2 devices. Okay, how to do the demos yourself. The first step, I would say, is actually to take a look at our general Getting Started guide, which is the very first link that I have there under Getting Started with Amazon FreeRTOS. And that's kind of agnostic of what platform you're testing or which of the demos you're running. That's how kind of you generally get started with Amazon FreeRTOS and AWS IoT. Very step-by-step, walking through, trying to make sure that you have a good experience with getting signed on to IoT for the first time, creating your first device or thing, and then getting that thing connected, or getting that device connected to AWS IoT, and doing your MQTT operations, kind of in a very smooth sequence, let's say. I do recommend starting on the Windows simulator, the caveat being that, of course, doing anything production in IoT, you're not going to be using a simulator, you're going to be using real hardware. So kind of the second step always is to test on your real hardware. But I do find the simulator to be very straightforward to debug. It happens that I've been using Visual Studio for a lot of my career just because I came from the Microsoft side. So it's actually really convenient for me to do kind of rapid prototyping with Amazon FreeRTOS in the simulator. But again, there's nothing like testing on hardware, and so that's always kind of the second step. And we have Getting Started guides both for the simulator, but also for all of like the 20 or so IoT developer boards that we've exhaustively tested with all of our libraries and all of our connectivity use cases with AWS IoT. Each one of those has its own Getting Started guide. Okay, so we're not taking questions, interactive questions, as you guys probably realized here. But as soon as I pack up my laptop, I'm happy to take questions off to the side. But until that time, thank you very much. I really appreciate you guys coming.